on the next slide a little bit more explanation for that. But like the other kind of memory corruption is when you imagine you allocate some buffer again in the memory, and then imagine you have like 2 pointers pointing to this buffer. And if you start freeing the buffer via one of the pointers, and I don't know, set it to invalid, then you still have a second pointer that is pointing to the now freed memory. And because I have no way of knowing that this one's actually freed. And if you use this memory, then you run into like a situation which is called use after free. And this can be a problem because you could imagine like between freeing it on the one side and then reusing it again, there could be like maybe even another case where you allocate again some memory and then it gets again allocated to the same type, to the same memory location. So the use of this pointer will then result in accessing some memory where you actually could have unexpected data, and you might interpret data differently than what it was intended. How this looks in a program would be quite simple, like what I basically just mentioned. Like you copy, you allocate some memory, and then you free it in the middle, and then try to, for example, copy some string into the memory. The reason why this is bad is because an attacker could make it in a way that he doesn't overwrite just like any random data, but he overwrites actually important data. In particular, what we're talking about are code pointers, which are, for example, interesting. The reason, and this is then called control flow hijacking. So the reason is, let's consider like a super simple program where you have a main function, the overflow function, which has this buffer overflow vulnerability, and you have this print admin password. In this program, the print admin password is actually never reachable because you probably don't want to print the admin password. However, if we now execute this program and an attacker can provide arbitrary input, the overflow function will be called, and the argv1 is basically if you write on your Linux command tools program name and then the first argument, this is like the argv1. So you can specify like a string there and pass it to the overflow function. When this function gets called, and now we have to go a little bit into like how this actually looks like from a memory perspective. You will have a stack, and on the stack you usually store, for example, local variables or function arguments or temporary values, things like that. And if you call the overflow function, actually the first thing that is done when the overflow during transferring the control flow to the overflow function is you write the return address, so the instruction that should be, or like the location that should be executed after the overflow function finishes, which should be executed. So in this case, it's line 8. So this is why I made the 8 there on the stack. And next, it will allocate actually the buffer that is specified in line 2. So here in this case, it's a buffer of 10 bytes, and this will be then also allocated on the stack. And then it's actually already the string copy function will be allocated, executed. So in this case, as I mentioned before, like the attacker can control the kind of input, which is basically a string, and what he can do when this is executed, then the string copy, the string copy, it will basically copy a string into the destination buffer, which is SB, from the source buffer, which is BB, the big buffer in this case. And the attacker can set an input that is bigger than 10 bytes. So in this case, it will actually, the string copy function will not check the bounds of the small buffer, but it will just write everything on the stack and thereby overwrite the return address. The attacker can be actually, in this case, a bit clever if they know the address of the print admin password function. they can write this address on the stack. And as a result, when the function wants to return, it first cleans up the stack, so removes, deallocates the small buffer, but the return address is still there. So the next thing is like the return instruction actually reads the address from the stack and then suddenly executes the print password function. That is like the very basic idea of like how control flow hijacking works. This is how it works, I would say, around like 2000. These days, it's often a little bit more complicated. That is because we have also more complex targets. So some people in Google actually found in iMessage a number of memory corruptions and also found a way to exploit this over the network. So they can basically send you some messages and then start execute or controlling the control flow, and then by doing so executing arbitrary code. And this might just crash the device, but they can also, for example, introduce malicious behavior, like, I don't know, sending all your text messages to a server or something like that. And this sounds scary. It is pretty scary. There are actually companies that pay money for this kind of vulnerabilities, or the exploits that you develop for these kind of vulnerabilities. And I'm not sure if you can read it, but it's like for iOS, it's actually between like 1.5 up to 2 million. And this company is actually like not the one that like pays out the most. There are other companies that pay even more. So I hope I convinced you somewhat that memory corruption vulnerabilities are important, and it's important to somewhat tame them. And here I have actually an example that I encountered also in real products before. This is just to demonstrate, just to give you an example that even this one is pretty simple. It's actually quite hard. It's not easy to spot what is the issue. Actually, it has multiple issues. But to give you like an idea, I will give you like half a minute, or like while talking, you can try to figure out if somebody knows a little bit about this topic, what's the problem here. But in general, what this function does, you give it also like a string as an input, like A, B, C, D, E, F. And what the function will do, it will always print out something like 1A, 2B, and so on. And the way it does this, it uses this sprintf function, which is a function that prints a format string or a formatted string to a buffer. So in this case, again, we have like some buffer allocated, which is in line 6, which is 16 bytes. And we then set a pointer to this buffer, and then in the for loop, we iterate over the input buffer and then write this to the destination buffer. In theory, that could be safe because we're using this SN_printf function, and with the SN_printf function, you can specify the number of bytes that should be written to the destination buffer in the second argument. And in theory, this should prevent any buffer overflows, except that the function behaves a little bit different than one might intuitively expect. So it returns always the number of bytes that would have been written to the buffer. So this can mean two things. In case the write was successful, it returned the number of bytes that are actually written. Or in case it was not successful, it will still return the byte that could have been written. And this is not like, as I said, not super intuitive. And this is why there are actually quite a number of programs or applications that do this or handle this case wrong. Because what will happen here, if I specify a very long string, the for loop will continue to write to the buffer, and at a certain point, the like size of buff minus Sterling buff will be 0. So that means there is nothing that can be further written to the buffer, but it will still return 2 because would have been could have written 2 bytes. And then in the next line, in line 11, you actually add this number 2 to the pointer, and so you run out of bounds at some point. So this is even though it's a pretty short and simple example, it can still have serious implications because, like in the previous example, you can take control of the control flow. And actually, one thing that another thing that is wrong with here is that the buffer is actually not initialized with 0. So the buffer, how it's allocated there, could contain random data, which again could cause problems in this case, because then the string length will not behave how it should behave. So yeah, these are just some example to show you that this is actually a pretty tricky problem. And I mean, it's known since, I guess, the 80s, 90s, that this is an issue, and we are still having trouble with this. But of course, over the time, people thought about different ways of how to mitigate this memory corruption vulnerabilities. And one thing that actually works quite well are safe languages. So C and C++ are the major languages that have these issues. And there are a number, as you probably know, there are a number of other languages out there which you could also use, like Rust, Go, which have actually similar-ish performance than C and C++ applications, or you also have Java. I wrote here that I say that like the best way of preventing memory corruption vulnerabilities, but the truth is even these languages can contain memory corruption vulnerabilities because the library that exports, for example, functionality, like implements Rust functionality, is still some of it is written not in memory safe languages, or like the Java VM is written in C, and is also very famous for having vulnerabilities there. And but these are like minor. Let me put this: it doesn't happen too often. It happens, but much rarer than like vulnerabilities in normal C and C++ code. But there's a problem. It's often not so easy to use these languages because existing projects often depend on libraries that or code that is written in C and C++. And if you extend the library like with a new feature, you often, I don't know, don't write it in a new language, but you use the language which the library is already written in. So extending with new features then again adds more C and C++ code, which again usually adds more vulnerabilities. And because rewriting the whole thing from, I don't know, in a new language can be expensive, and you also probably will have like compatibility issues with like existing code that is depending on that. The other thing is that mixing memory safe and memory unsafe code can lead to problems as well. And the reason, to give you a very quick example where this can lead to issues is, say we have like our memory safe language, which represents a string in memory as an object, which has a length and a pointer to the actual string, like hello world. And the way it is done in C or C, mostly in C, is that you just have a pointer to the string. And the way you know that the string is like done is you put a null byte in the end. So now imagine you forward a string from your memory safe language to a C library and don't do any modifications there. The problem is that most of the C functions that I don't know work with strings are expecting that there's a null byte in the end because they were written in a time where this was normal. So what can happen if you forward like this memory, the string hello world from the memory safe to the C, is if you have like your super secret password, some random data, and then the null byte in the end, and I don't know, you have just some function that processes the input, it will not only print the hello world, but also your super secret password, some random data, and then stop. So this is also like issues we actually have seen like examples in the past where this kind of things happened. Another way of mitigating vulnerabilities is just finding all the bugs. Humans are actually not too bad at doing this, but they don't scale. And they also get exhausted at some point. So it's not like a super good thing. It works, but it doesn't scale. One thing that Google is doing is it offers so-called bug bounties, which is basically we invite you to look at like all the products, try to find vulnerabilities. You can submit them to us, and then we pay you some money. Then there are approaches that use automatic tools. Static analysis is one way of doing this. Static analysis, from my experience, has the issue that either you specify exactly what kind of bug and what kind of code base you're looking for, and then it might find like some variants of an existing bug. Or you make it a bit broader, the rules a bit less clear. Then you will get like a high number of false positives, and it can be pretty mentally like pretty exhausting to go through a list of, let's say, I don't know, 200 results where, I don't know, 95% are false positive, and then you need to spot like the 5% of vulnerabilities. At some point you get like a certain fatigue, and then you might even miss a real vulnerability. So this is also not like optimal. However, if you what I mentioned earlier, if you have like something where you have like a concrete instance of a bug and you just try to find variants of that, in this case, static analysis might actually work quite well. Another approach are like dynamic tools. Fuzzing is probably like the most prominent example of that. This is basically you generate a bunch of more or less like random input to the application and then wait until it crashes. Because if you have a crash, then it's most likely something that was not intended. Often it is, like in the case of CEST++, this is actually a memory corruption vulnerability. Google has good fuzzing infrastructure, also for open source projects called OSS Fuzz, which over the years found more than 16,000 bugs, which is pretty good. And the one, it still requires a human to create the fuzz target, so the thing that actually is feeds the generated test cases to the target application. But this is much more scalable than like manually looking for bugs. And again, here, if you write fuzzers for OSS Fuzz and they find bugs, you will get money. Then there's a third category, how to mitigate these memory corruption vulnerabilities, which are like actual mitigations. So I wrote a bunch of like acronyms there, like ASLR, CFI, CPI, PEG. They are all like they're like different approaches. One are like trying to like randomize the memory layout. So if you think about the first example where you try to jump to the print password function, if this one is like at a random address, then the attacker might have some trouble to guess this address. So this is like one kind of defense. Then we have also like more like policy based defenses, CFI. So before you take actually the return, you will check, is the jump allowed to the like print password function, or should I return not to something else in this case? Or like PAC, which is using it's called pointer authentication codes. This one's actually pretty hard to bypass, although people have been also showing that it's possible. It's basically signing like with crypto the pointer and then validating it before it's used. One disadvantage is that the performance overhead of these mitigation can be quite big. You have like very cheap ones like ASLR. This, I don't know, I think it's like every modern system actually implements this. It's quite cheap. It's like below 1% overhead, but you can also get like to quite expensive ones, which are like 10x overhead of, and it might be okay like in certain cases where like you really need to have like maybe like bulletproof code, but it's like if your browser becomes 10 times slower than now, then that's probably not desirable. And even though they're mostly designed in a way that you can just plug and play them, it's often the case that it requires some refactoring of your existing code to make it work. Yes, and despite all that, we still have memory corruption vulnerabilities. So sandboxing is actually one way of significantly reducing the risk of memory corruption vulnerabilities. If you have like a vulnerable application, like on the right, this vulnerable application usually needs to interact, like, I don't know, with other processes, with files, or like with operating system. And the idea of sandboxing is to create an isolated execution environment which has very low privileges. And the assumption here is that the application running inside the sandbox actually can be compromised. So you want to make a security boundary around the vulnerable application, even under the assumption that the attacker can execute arbitrary code. And the way you do this is you insert like some abstraction layers in the between accessing to the resources and the vulnerable application. And now we're going to talk a little about how this is done in Linux, and actually how also, I mean, this is what we're also using, this kind of sandbox. Linux offers something that's called namespaces and seccomp. These are like two features that are like built into the kernel that you can use to isolate a process. So generally, namespaces create an abstraction layer between for the system resources. So if you have like our global namespace, like here, like with different processes, you can like create two namespaces. For example, in one you put process A and B, and in the other one the rest. And the result is that none of the processes in the one group can see the resources of the other group. And the Linux kernel offers this for like a variety of resources, like mount so files or processes network or like user namespaces. And you can even have like nested namespaces. So like in the namespace of process A and B, you can put process B in a separate one so that the process B can't access any resources of A. You can actually try this also if you have a Linux machine attendant. You can also try this. I executed here two commands, two times the same command. One time outside of the sandbox, one time inside the sandbox. On the top is outside of, not sandbox, I should say namespace. Here you can see that PSAUX just shows you the current processes. And yeah, you can see like a bunch of like kernel threads actually, and worker. And if I use this unshare command and create a PID namespace, what you can see here, if I, and the -u is for user, if I then execute the same command again, like the PSAUX, there are two things you can see. First of all, like I'm no longer the dev user anymore. I'm now the nobody user. And the second thing, the PIDs, even though they have like the same process ID, it's for different processes. So this is what I was mentioning before. Like we have like now a different, we have an abstraction layer, and now it looks a little bit different from inside of the namespace. The seccomp filter uses actually can filter system calls. So if you want to open a file or open a network connection, this is when you do a system call. And the seccomp implements or allows to define rules in forms of small programs, which then, for example, I don't know, can return true or false. If, for example, if the system call should be permitted or not. The advantage of these things is this Berkeley packet filter. It says packet filter. It was originally created for networking, but you can use it for other things as well. It's like, as I said, small programs, and you can define a filter in that, and then for each system call, this filter then will be executed, and it will be checked if the system call is allowed or not. So this is it's a nice way to allow or disallow certain system calls, or you can even allow system calls for certain resources. For example, you can say, I don't know, you can only open files for read access, but not for write access. These things can be also a little bit tricky because the system call numbers between different architectures can be different. So I don't know, on x86 this can be different than on PowerPC. For example, I'm not sure like where they actually differ, but I know that like you need to be careful to double check that. Another maybe fun fact, like the Berkeley packet filters, they're supposed to be safe. Like you can't create a filter that actually compromises the kernel. Unfortunately, again, someone from Google actually showed that this is not necessarily true, and that this one can have issues as well. But again, this are like while there are severe issues, they're not that often. Again, like if your random C and C++ program will have more likely vulnerabilities than this one. Finally, we have C groups, which do like some resource control. So for example, you can allow that the program running inside the sandbox can have only, I don't know, 100 megabytes of memory, or can execute only a certain amount of time, or only has like one core available, or I don't know, can maximum open 20 files. The reason why you want to have this is because you can also sandbox process like applications that not necessarily you assume have vulnerabilities, but which you in general don't trust. So you might have like some random application you download from the internet, and you want to execute it, but you want to make sure that, I don't know, it's not mining Bitcoins or something like that. For this, the C groups are quite handy. So let's have a look how this could work in practice. We have here our cool user application, which we want to sandbox. What the application is doing is just getting memes from the internet and put them into PowerPoint presentation to make them better. So what this application needs to do, it needs to be able to first like download the memes. You probably need a way of process the PowerPoint presentation. So that's why I say we parse the PPT, and of course you need to like also open the file and write the file, and you also need to parse your memes, which maybe gives. So it requires network access, accessing files, access of different directories. And if you think about this, even if you put it into a sandbox, and you need to allow certain functionality, right? So you can't just disallow that it can't do network connection, because then it can't get the memes. So in this case, you need to give it access to the network and so on. And this is actually not very desirable, because let's say we have a vulnerability in the parse GIF or parse PPP function, then if the attacker can provide like some malicious file, hijack the control flow and so on, he will be still able to read like all the user's files and send them to the internet, or like even connect to other services or applications that are running locally and escalate privilege even further. So this is clearly not ideal. Even a sandbox in this case wouldn't do much. This was also one of my thoughts when I was writing my thesis. Basically I wrote that it would be cool if we have like some way of taking like only the part of the program that is likely to contain vulnerabilities, take it out, put it into like some isolated environment. Ideally, everything should be more or less like automatic. This is what I thought could be nice future work. That was before I joined Google and learned about Sandboxed API, which is basically implementing all of what I thought. And actually, I don't know, maybe 1 year ago or something, it got open sourced. So now everyone can actually use this. So that's pretty cool and exciting. What the Sandboxed API is doing, it's somewhat like the name hints at. you can sandbox APIs, so parts of a library, for example. And the main goal is that it's easy to create a sandbox, like for certain C and C++ code, and to only isolate really the part that is likely to suffer, like from memory corruption vulnerabilities. It is based on the Sandboxed 2, which is the thing I basically described before, the one that's like using namespaces and seccomp. And it provides a library that generates like more or less like automatically an interface for you. So you can take like your existing library code, just specify I want to sandbox this part, and then it will generate like all the necessary code around it, and also handle things like provide an easy interface for like configuring the sandbox, or like handling the communication between the code that's running inside the sandbox and outside the sandbox. So what this allows us to do is to, instead of having like this parse PPT and parse GIF in together with all the other functions in one sandbox, we can decouple the functionality and put it only this code into the sandbox, which then allows and then I don't know, generate some stuff so that only if we can already like download the meme, and then for parsing we send it into the sandbox. Even if there's like a memory corruption, it will be like inside the sandbox. And then if everything was good, we can send the results again out. The big advantage of this design is that the sandbox in this case basically needs no privileges, or like it doesn't need to read any files, it doesn't need to open network connection, or it also doesn't need to do like any other fancy system calls, maybe except by allocating memory, but we can also like pre-allocate memory there. So the advantage here is that the code that is likely vulnerable runs at like basically no privileges at all. This gives you like a little bit overview of like how the internals look. So you have like your in one process you have like your original code and the interface. Then you have like the policy builder, the code that is generated and interacts with the sandbox, and your monitor. This then creates a separate process called a fork server, which then starts actually the code that is potentially vulnerable, and it allows like easy communication between like the interface and the actual code. And it has also like some other sandboxes that, I don't know, if something crashes, then can safely take the stack trace and check and parse this one and give it back to the user. Let's have a look at a short example. Say you want to sandbox this sum function, which just adds two integers together. If you create, if you specify that, basically the only thing you need to do is instantiate the sandbox, and afterwards you can call it like a normal function. It looks a little bit different, admittedly, than what you like. How would you call the original? But I would argue it's pretty close, and it's not like too much work in this case to refactor the code. This one actually generates some code, which is like the interface, which is api.sum, which looks like this on the right side. It's nothing important, just like in line 19, basically. This one gets calls into the sandbox and then also gets like the return value back. So, but this happens all like behind invisible to the user. So for the user, you just have like the interface and you can call it, and then anything happens inside the sandbox shouldn't really matter. The way you specify policies looks like this. It's also you specify like a policy builder, and then you can I don't know, specify like some system calls that should be allowed. So by default, everything is disabled, and then you can like put something on the allow list. And of course, like for our sum example, you probably wouldn't need to read and write files, so you don't need the system calls. I think this was a policy for something else. And you can also then allow like access to certain files. So any, like from the sandbox point of view, if it wants to access like any other files on the file system, they're like just non-existent. And I created this sandbox and then executed. I assumed like I got arbitrary post execution in there and wanted to spawn a new process. And since this is not allowed by the policy, it will print me a sandbox violation and then also, I don't know, give me some more information like how this was caused. So yeah, there. As everything what I mentioned so far, this one is like also not like, of course, not 100% safe. So they're like, it's pretty safe. But if you are not careful while configuring the policy, like your policy is too permissive, as mentioned before, then the attacker might be able to do certain things. And there are 1 or 2 system calls, which in a certain configuration,
Christopher, I think you're on mute.
How did that happen? How long was I on mute?
Like 10 seconds or so.
Okay, so you got most of it. That's good.
Yeah.
Sorry for that.
No problem.
Yeah, as I said, so for the policy configuration, you need to be careful. Don't don't allow certain system calls as they would allow to disable the sandbox. There are like some files which you need to be careful, don't pass into the sandbox. And one very important thing, everything which comes out of the sandbox, so everything like as a return value, you need to check that this one is not like in a weird formula. So you need to sanitize it because you need to assume the attacker can just give you arbitrary things outside of the sandbox. And this might, again, trigger code that is processing the output of the sandbox. Another thing are kernel bugs, since the sandbox is based on the kernel on functionality. If you have a bug there and it's reachable from within inside the sandbox, the attacker might be able to bypass that as well. And you probably also read like about like CPU bugs. Of course, in this case, the sandbox also wouldn't help you. Just quickly go into performance. There is some performance penalty, especially if you I don't know, start a new process very often. This adds up. But if you do this like one time, even if it's like goes to 200 milliseconds, I think that's an acceptable performance overhead. System call filtering actually also introduced some overhead. But if you assume that like from the sandbox code, it's not supposed to do any system or many system calls anyway, then you might not care if this adds some overhead. There currently is some challenges we are working on, which is to make the interface generation code even better, to work with like other languages as well. We're working on improving performance and trying to make it adopt to like other operating systems and platform. Currently, it's targeted Linux. And yeah, so to conclude, Sandbox tool and Sandbox API are pretty good for reducing the attack surface of CMC++ programs. And Sandbox API is pretty good for like isolating only like critical part of the code. And also good news is that if you start sandboxing popular libraries, open source libraries, you can also submit this to our patch reward program, which again pays you some money for doing so. Because I think we like also rely on some like open source libraries, so we're happy like if these get safe as well. So yeah, is this a silver bullet to deal with memory corruption vulnerabilities? Unfortunately, no. It's pretty good, but it doesn't solve the problem. The idea is still to like move away from languages that have these issues. We continue fuzzing to find as much as vulnerabilities as possible. Mitigations, yeah, it might work in some cases. There are certain cases where we know it doesn't work very good. But yeah, it depends a little bit on the use case. There might be cases where this actually works quite well. All right, Here, like some pointers also like to Sandbox API, to the open source one. So yeah, that concludes my talk. I'm well happy like to answer any questions if you have some.
Thank you very much, Christopher, for this very interesting talk. I didn't know that Sandboxed API existed, but it sounds and looks very interesting and convenient to use. So we do have quite some questions, actually. And
All right.
just a side note, I'm really happy about the number of watching people on YouTube. So this basically doubles the number. Yeah. So the most upvoted question was, can you send us the link to the slides? Because I noticed there are quite some links and some of them weren't typed out. So would this be possible to send it around?
I will probably need to double check this. My guess is yes. And I will definitely send out all the links because they should link to like public stuff anyway. So yeah, I will see that I get you the slides, but the links I will definitely get you as soon as possible.
That would be nice. Yeah, thanks. Cool. So just send them to us via email, and we will distribute them to all of you in the streams. So this is answered, I would say. Another question, super interesting, is it theoretically possible to break out of a sandbox? And I think more specifically out of Sandboxed API?
Oh, it's definitely possible. Like what I mentioned, this so this is actually one quite misconception. Like people think they enable sandbox, this is sandbox, and then they're good, but they don't check like what's coming outside of the sandbox. So they treat again this the output of the sandbox as trusted. And if like if you have vulnerable code that is like processing the output, you can do the same game again. So Sandbox API is really just to like reduce the attack surface in general, but you still need to be careful. So this is why I was saying it's not like silver bullet. You can still have issues.
Sure, sounds reasonable.
And the sandbox might even have vulnerabilities. We try our best not to introduce some, but there might be like edge cases that we miss. So you're also very welcome to look at this code and try to find vulnerabilities in there.
So Sandboxed API is probably also written in C++, right?
Yes.
Okay. Would be interesting if it was in Rust, and then you could use it in C++, maybe.
It should be possible.
Cool. So what is or what does the roadmap of Sandboxed API look like?
Yes, it's basically the what I mentioned more or less like in the end, like making the interface generation code. It's already doing like compared to like everything else what we know of, it's working quite well, but there's like always room for making it even better. So yeah, and like different platforms is definitely something that we are like very interested in. Linux covers like most of our many use cases that we have, but yeah, more is always better.
But isn't it super hard to port something like this to, for example, Windows?
Exactly, it is because you have like completely different ways of actually implementing sandboxes on Windows versus Linux. So yeah, it's quite challenging to have like a similar interface, I would say.
Sure. So another question. You mentioned that as a fun fact, the number of system calls is different on different architectures. So what are the implications of this, and how does it relate to like something like Sandboxed API?
Yeah. So yeah, it's actually not only the numbers of system calls, but also like system calls. Each system call has like a number, like from 0 to upwards. And like for example, the open system call is, I actually don't know by heart, but let's say 10, and it can be like 11 on a different architecture. So if you implement Sandbox API for like x86 and you say, okay, open is always like the 10 and I don't want to allow this, and then you suddenly take the same sandbox to like another architecture where 11 is the right system call number you should block, suddenly you're not blocking open anymore, and then the sandbox will behave differently on different architectures, if this makes sense.
Okay,
so
yeah.
That's not good.
So, and jumping to the beginning of the talk, you mentioned control flow hijacking.
Yes.
And one question on this was, so control flow hijacking like this is only possible when using the stack, right? If my array was on the heap, for example, with malloc, I can't overflow in return addresses, right?
Yes. So this is true for return addresses. Unfortunately, this is not like the only kind of function pointers that is stored in memory. If you think of, for example, vtables in C++, basically you have them like when you have virtual function in inheritance, and you need to figure out during runtime like which actual function you need to call, like whether it's like from the I don't know, parent or like the child class. These are also function pointers, and they get stored on the heap. So you can do the same game also on the heap. But yeah, you're totally correct. Like you don't have return addresses on the stack, hopefully. So yeah, there wouldn't work return addresses, but there are like more than one type of function pointers there.
Okay, that's interesting. So when I have an array or vector, basically a vector, right, of base classes, which use like inheritance and vtables, then this would still be possible.
Yes, and you can even think of like other things. Say you have like a variable on the heap, which is marking or like saving a global state whether the current user is admin of the application or not. And this is like just, I don't know, a Boolean variable, so either 0 or 1. And if you can override this one as well, like from is admin from false to true, then you can also like, even without like hijacking the control flow, you can still do malicious things. Other ways would be, I don't know, if you can just overwrite the length value of a string, and then suddenly you can leak memory which contain, for example, SSH key or something like this. So there are like a bunch of ways how to exploit memory corruption vulnerabilities.
Super evil stuff. So speaking of mitigation, would it be feasible to put every single process in its own C group? Or would this be too slow, or would this have some other implications that something wouldn't work anymore?
I mean, processes by itself, there are already like isolated from each other. So you probably don't get, like in terms of isolating the processes from each other, any benefit. If you put it into C groups in terms of you want to limit like resources, this is certainly possible. It might lead to crashes of certain application, like your web browser, if it like asks for more and more memory and it's limited, and then at some point, I don't know, it stops working. So I would say, like from a security perspective, maybe it can do something, but you would like probably put applications into like restrict applications that don't expect to be restricted, and they would just crash.
Oh yeah, sure, yeah. So I sometimes do have the same problem with packaged applications on Linux. So another super interesting question. So currently solutions like ARM Trust Zone are very trendy. When using Trust Zone, would a sandbox improve separating the secure applications to avoid takeover?
So yes, so ARM Trust Zone is basically you have like a somewhat like a second execution environment, like a normal execution environment on the same processor, only that it's can't be accessed like from the normal world. So we have like two different environments. Inside of the secure world, you can run your own operating system, your own processes, and it probably makes also sense to have, if you do like something like parsing inside of the secure world, like an ARM Trust Zone. I don't know if you parse your GIF there, then it probably also would make sense to apply sandboxing there as well. Yeah.
Okay, cool. Completely different question. Would it be possible to also handle or mitigate some of the hardware vulnerabilities by the Sandbox API, or is it something planned in this direction? Or is something planned in this direction?
That's a good question. I think you might. So generally, the answers I think would be unfortunately no. Like the sandbox is also like somewhat relying on the CPU to do its job, and if this one is vulnerable, then it's difficult. But you might be, in some cases, able to, I don't know, restrict the code that is inside the sandbox in a way that some of the requirements for executing the CPU attack are not fulfilled, if that makes sense. So it's not like directly you avoid it, but like you can somewhat mitigate it. I don't know, for example, like if you need like 2 cores to do the attack, or like hyper-threading, and you disable it inside the sandbox. So that would be one way, but yeah, you don't necessarily need the sandbox API. It's maybe possible, but it's I wouldn't say it's like a core feature.
Okay, cool. So one question where I really can't say anything about it because I don't know the topic, but I just read it. What do you think about simulation theory? Not sure what it is, though.
It's feasible. It's certainly possible. It's about that we are like all living in a simulation. I think there's some good arguments to be made for it. If anyone doesn't know it, I would recommend to read up on it and get some information on it. It's pretty interesting. I would say that it's like there's a non-zero chance it's happening. Yeah.
Sure, there's always a non-zero chance. So last question, or for now at least. So if there are people who still have questions, feel free to unmute afterwards or type them in the chat as well. So what was your role at Qualcomm?
I was in incident response, which is basically was doing like if there was like ever like anything wrong with like any vulnerabilities, then we start take a look at it and start handling it, and like I don't know, contact the teams for fixing it. It's similar, like I think we handled like the bug bounty program. So if people submitted the bugs, we started investigating if there's real bugs, like what are the implications, and like as I mentioned, see through the process of getting it fixed, and also like I don't know, work on mitigating certain classes of bugs, I would say.
Okay, cool. So thanks a lot for answering all these questions and for your time and for the interesting talk. So what's left to say is, thanks a lot again. It was very interesting. And yeah, I'm not sure if this works here because sometimes it does. It depends on the audience. So because this is online, it's really hard to like give an applause, but we can try to unmute ourselves and give at least a quick applause to you, because I think it was, again, very, very nice to have you here. So thank you.
Thank you very much for having me.
Yeah, nice.
Very good.
Cool. So, Flo, would you like to take over and not sure, say some last words?
Well, thank you also from my side, but I don't have anything else really to say, except we have another event upcoming in a few weeks, which is a talk about WebAssembly by Andreas Zimmerer, who is also in the meeting with us right now, who just talked. And so you can sign up on the DSC page again, and we would love to see you there as well.
So thank you for having all of you here, and bye. See you next time.
Bye.
Bye-bye.
Right, thanks. Bye-bye.
Bye. Bye.
Bye.